All right, last one. So we were talking about the Doppler effect. When an object is coming towards you emitting a frequency, it makes a higher pitched sound. You interpret it as higher pitch. When it's going away, you interpret it as lower pitch. Obviously the object, this ambulance, is not changing its pitch just for you. This is something that is happening to you for another reason, not because the ambulance is changing its pitch. Let me go. Okay, so I'm going to erase this actually, and then I'll bring it back. We're going to write kind of a lot under Doppler effect. So let me erase this and let me show you a little clip that I just found, or a little animation, I should say. Excuse me. Not that. Okay, Doppler effect. So hopefully you can see on here. Can't I zoom in? Okay, so what we're looking at here is this red dot. Maybe if I turn the lights off, it'll look a little better. Okay, hopefully you can see this. There's a little red dot. And what I'm going to do is I'm going to hit play. And this little red dot is emitting a certain frequency. Okay? And these, so imagine sound waves. Okay? Little red dot is emitting sound waves and they are moving out at a regular rate. And since this little red dot is not moving, sound waves are spreading out in concentric circles, circles that are all centered around where the red dot is. Okay? That's what sound waves look like, and they kind of die off as they get farther away and they dissipate. Nothing is reaching our microphone right now. If I let it reach the microphone, so it's making a sound every time the wave hits the microphone. Now let's do this. Let's try giving it some, that's not what I want. Let's give it some speed. Let's let it move. I want you to watch the sound waves. They're not concentric circles anymore. Matter of fact, they're kind of squished on one side because the object is moving as it's creating these circles. So we have wave fronts, basically wavelengths, that are more compressed on one side. So, did you see what happened? We can try it one more time. As the object moved, in front of it, the wavelengths, they're called wave fronts technically, we learned that last year. The wave fronts were more closely spaced together because the object was moving in that direction. Behind it, the wave fronts were more spread out. So when the wave fronts were closer together, the wavelength was shorter. We interpret that, the microphone interprets that as a higher frequency. You heard more sounds per second. When it gets to the other side and the object's moving away from you, you hear it less per second. Okay? The wavelengths are bigger because the wave fronts are more spaced out. One more time. Let's see it. Okay. Shorter wavelength, bigger wavelength. Detected frequency right down here. Not the same as the actual source frequency. Interesting. Okay. And actually, if I take this microphone and I move it around, I think, oh no, I guess it doesn't. Okay, I thought this was better than it was. Darn, that's what I get for trusting in technology. Okay, but anyways, we see the basic point, okay? The reason the Doppler effect happens is because those waves are much more compressed than, why did I open the door? Those waves are much more, on one side, they get much more compressed. There's a shorter wavelength than on the back side. So shorter wavelength means higher frequency. Longer wavelength means lower frequency. That is where this illusion, I should say, is coming from. Doppler effect is an illusion that happens. So let's draw a picture of this. All right. Here is our source. Now this is tiny writing, but you can deal with it. Source is moving this way, and let's say maybe the wave fronts for that source look something like this. Alright, that's not a very good one, but you get the picture. Okay, you know I can't draw. But notice that, here's our observer. These are still relatively circular. The wavefronts, if you look at that simulation again, are all relatively circular. Okay, they should be perfectly circular. It's not that the wavefronts themselves distorted, it's that the source kept moving and moved while this wave was spreading out, while this wave was expanding circularly. So, what it does is it compresses, it makes the illusion that the wavelength in front of the source, or in the direction the source is moving towards, is less than it should be. The wavelength back here is bigger than it should be. So let's write that down. So we've got wavefronts in front of source. And the word I like to use is that they get squished. As the source moves with them. The source moves with them, and in the example that we gave, the source moved with them more slower than normal. This actually works up until and including past when the source actually moves faster than the wavelengths. We just call that traveling at or beyond the speed of sound. That's what that is. So, because the wavefronts, meaning essentially that create the wavelengths, get squished, smaller wavelength becomes a higher frequency. Or at least it seems like a higher frequency. On the other hand, behind the source of the sound, it works the opposite way. This not only works if the source is moving, it also works if the observer is moving. Okay. Also works if observer is moving instead of the source. Now, believe it or not, this is not really something that I am going to be very concerned with. There is an equation that describes the frequency that you hear in the Doppler effect. There is an equation that describes this. It is not an equation you need to know for the test, I don't think. It's good to know, and there is one homework question that is pretty much impossible to answer unless you have this equation, so that's why I'm giving it to you. The equation for the frequency heard by you, the observed frequency I should say, so we'll do f prime. This is the observed frequency. Is as follows. The observed frequency is equal to the actual frequency multiplied by a fraction with lots of stuff on it. I'm just going to write it down, then I will explain it. V sound plus or minus V observed, or V of the observer. I'll write that in. And then V sound plus or minus V source. Okay, so that looks kind of crazy. You're like, what the heck? There's pluses and minuses in here. What gives? So, plus or minus depends on what's actually happening here. So the observed frequency is equal to the actual frequency times some fraction. Okay? If the observer is not moving, then this is 0 and this is just the speed of sound. If the source is not moving, this is just 0 and this bottom part is just equal to the speed of sound. However, if either the observer or the source, or both, are moving, that dictates, and which way they are moving dictates whether we do plus or minus on the top or the bottom. So, on the top, we think about the speed of the observer. In the little demonstration there, that was a little microphone, speed of the observer. We use on top a plus if he's moving towards source, and a negative if moving away. That makes sense. If the observer is moving towards the source, you would expect to hear a higher pitch. We would want to make the numerator bigger. If he's moving away from the source, you would expect to hear a lower pitch. He's not getting as many wave lengths coming to him as quickly. They seem more spaced out. Frequency seems lower. So that part makes sense. Positive, this is a plus sign if he's moving towards the source, minus sign if he's moving away. On the other hand, on the bottom, this is the speed of the source. The speed of the source also dictates, and which direction the source is moving also dictates plus or minus, but it's reversed. Speed of the source is negative if the source is moving, let's see, it's negative if he's moving toward observer. And it's positive if moving away. So why would that be? Why would it be reversed? Look at the equation. If the source is moving towards the observer, that's a higher pitch, right? Well, how do we make the bottom account for a bigger observed frequency? We would have to make the bottom smaller. So that's why it gets a minus sign. If, on the other hand, the source is moving away from the observer, we put a plus sign. That will make this that will make the bottom bigger. That will make the observed frequency smaller. Like I said, this equation is complex. It seems complex. It's really not once you use it. I used this a couple times in college, and that's really it. It's not something that the AP expects you to know. It's good to understand how it works, I think, and it's good for, like I said, one homework question. You kind of need to reason with this. You probably still get it wrong, but that's okay. I like the question. That is the Doppler effect. I think what I'm going to do is I'm going to cut this video, and we will go over principle of superposition in class tomorrow, because that is what we're going to spend the majority of our time on tomorrow, is superposition. We are going to do some real basic superposition here, and then I'll show you the sheet. Where are they? Here they are. I've got a couple examples made up on graph paper. You should know how to superpose on graph paper. So we'll do this one, and I'll give you this one for practice. And then we'll very briefly start off sound waves. We'll take a very brief introduction to, not sound waves, but standing waves, because that is going to be the majority of our focus for this waves unit. So, hopefully you have time to watch these. Like I said, it should be a little bit, right about an hour, a little bit more than an hour maybe. I guess that's it. So have a nice night. I'll see you tomorrow.